Hi everyone, this is Arash Asghari Vaskasi from the Existential Robotics Lab at UC San Diego. Today I'm going to present semantic octree mapping and channel mutual information computation for robot exploration. This work aims to propose a solution to the problem of active mapping, where we aim to autonomously build a low uncertainty map in real time considering the collision and visibility constraints under a limited exploration budget such as time or distance. In particular, during each planning step, our objective is to find the most informative robot trajectory by maximizing the mutual information between the map and the observations made along the robot path, discounted by the path cost. Imagine a robot equipped with an RGBD camera that provides color and depth images at each frame. Additionally, the object category of each pixel in the color image is obtained by processing the RGB input with a semantic segmentation algorithm. Adding the depth measurements, we define a range category observation as a semantically annotated point cloud, where the range is obtained from the depth image and the semantic labels come from the semantic segmentation image. As we receive the stream of sensor measurements in real time, we employ a Bayesian filtering scheme in order to integrate the range category observations into a multiclass octomap, where each node of the corresponding octree stores a categorical probability distribution over semantic labels, as well as information about its children nodes. The octree data structure allows compressing the environment representation since similar nodes in the octree can be pruned into a parent node, leading to significant gain in memory usage. During each planning step, the robot computes the boundary between the known and unexplored regions of the current map estimate. We call these boundaries frontiers. A candidate robot trajectory is defined as the shortest path between the robot's current location and the frontier. In order to evaluate the informativeness of each candidate trajectory, the robot needs to compute the mutual information between the semantic octomap and the potential range category observations made along the trajectory. We derive a lower bound for the mutual information, which involves summing likelihood terms of the inverse observation model over all instantiations of the potential range category observations. By exploiting the octree structure of the environment representation, we can compress each raycast of the observation using run-length encoding technique, where instead of storing the multiclass probabilities of each map cell along the ray, we simply store the groups of consecutive cells that share the same multiclass probabilities, plus the size of each group. This will lead to faster evaluation of path informativeness since it reduces the number of summation terms in our mutual information formula. A planning step concludes by choosing the trajectory that maximizes the objective function mentioned earlier. The robot executes the plan using a low-level controller, and it starts another planning step after finishing the current plan. In addition to 2D and 3D simulated experiments, we deploy our method on a ground-wheeled robot to autonomously map an indoor office area. The robot is equipped with an NVIDIA Javier NX computer, a Huhuyu LiDAR, and an Intel RealSense RGBD camera which provides 2D color image and depth map. We implement our software stack on the robot using ROS. The LiDAR is used for localization via ICP laser scan matching. A neural network based on a ResNet 18 architecture is used for semantic segmentation. Our pipeline was able to update the semantic octomap with around 3 Hz frequency on average, while all of the computations were performed under mobile robots. For more information regarding the derivation of the mapping and information computation, please refer to the main text. You can also find a short description of the work, the conference version of this paper, and the source code by visiting our website or GitHub repository. Thank you for watching my presentation.